The Man Who Saw the Invisible. Our story begins not in a laboratory, but in the warmth of a Copenhagen home in the late 19th century. Picture a family dinner, the air buzzing not just with conversation, but with ideas. A boy listens intently as his father and guests, leading minds of Danish science, debate the mysteries of the natural world. For young Niels Bohr, this wasn't a rare occasion, it was simply life. From these very beginnings, he was taught that to question the universe was as natural as breathing. And question he would. He would go on to peer deeper into the heart of matter than anyone before him, to draw a map of the invisible atom, and to champion a radical idea that would shake physics to its core, that at the fundamental level, reality itself is a matter of perspective. He was a thinker so profound that Albert Einstein, his greatest intellectual rival, would say of him, "He has the highest form of musicality in the sphere of thought." This is the story of Niels Bohr, the architect of the atom, the philosopher of the quantum, and the scientist who fled the Nazis with a bottle of heavy water in one hand and the secrets of the nucleus in his mind. Act 1. A Copenhagen childhood, where curiosity was king. Niels Henrik David Bohr was born on October 7, 1885, into a family where intellect and empathy were the twin pillars of life. His father, Christian Bohr, was a renowned physiologist, twice nominated for a Nobel Prize for his work on how blood carries oxygen. His mother, Ellen Adler Bohr, came from a wealthy and influential Jewish banking family and was known for her exceptionally warm and amiable nature. The Bohr household was a sanctuary of curiosity. Christian Bohr believed his children should be seen and heard in scientific discourse, allowing Niels and his younger brother Harald to absorb the debates of Denmark's academic elite. And what a brother Harald was! The two were inseparable. Harald, who would become a celebrated mathematician and even an Olympic silver medalist footballer for Denmark, was the lively, teasing counterpart to Niels' more thoughtful, deliberate nature. Their rivalry was pure affection. On one occasion, after Harald had teased him mercilessly, an adult intervened, only for Niels to immediately defend his brother. "Harald is the best brother in the world, and I like to be teased." Niels' own attempt at teasing later was so gentle, pointing out a small stain on Harald's jacket, that it only made them laugh. This bond was foundational. Here was Niels Bohr, a future giant of theoretical physics, who was also a passionate goalkeeper for his university soccer team, playing alongside his brother. He was never just a brain in a jar. He was a man who understood teamwork, both on the grassy pitch and in the intellectual arena. His father also gave him a deep love for precision and hands-on work. Young Niels was the family's master tinkerer. When a bicycle sprocket cracked or a watch faltered, the adults might suggest a professional. Christian Bohr would simply say, "Let the boy be, he knows what he's doing." And he did. This unique blend, theoretical grandeur discussed over dinner and practical mechanics in the workshop, forged a scientist who could dream of orbiting electrons while also building the delicate glass apparatus needed to prove his ideas. This was the forge of a great mind, a world of thought, play, and craftsmanship. But to change the world of physics, this promising young Dane would first have to leave his beloved Copenhagen behind, embarking on a journey to England, where a gruff New Zealander named Ernest Rutherford was about to shatter the very idea of solid matter. Act 2. The Quantum Leap. Mapping the Atom. Bohr arrived in England in 1911, a freshly minted PhD whose thesis on metals had already hinted that classical physics was failing at the atomic scale. He first went to Cambridge, hoping to work with J.J. Thomson, discoverer of the electron. It was a mismatch. Bohr, thoughtful and prone to deep doubt, didn't impress the more established Thomson. His salvation came in the industrial city of Manchester, where Ernest Rutherford had just performed a revolutionary experiment. By firing tiny alpha particles at a sheet of gold foil, Rutherford discovered that atoms weren't uniform plum puddings of positive and negative charge. Instead, they were mostly empty space, with a terrifyingly dense, positively charged nucleus at the center and electrons whirling somewhere in the void. It was a stunning discovery, but it posed a catastrophic problem. According to the unwavering laws of classical electromagnetism, an electron should spiral into the nucleus in a fraction of a second, emitting a continuous rainbow of light. In other words, every atom in the universe should instantly collapse. But they don't. Matter is stable. So what was wrong? Bohr, now working in Rutherford's vibrant lab, saw the problem with crystalline clarity. The old rules must break down inside the atom. He found his key in a nascent, controversial idea: quantum theory, pioneered by Max Planck. What if electrons couldn't orbit anywhere? What if, like a ladder, they could only exist on specific, discrete rungs, certain stationary states of energy? An electron could jump from a high rung to a low one, emitting a precise packet, or quantum of light. But it could not spiral. It could only teleport. In 1913, Bohr published his radical model. He applied it to the simplest atom, hydrogen, and performed a miracle. For decades, scientists had known that excited hydrogen gas glows with a specific set of colors, a spectral fingerprint no one could explain. Using his new quantum rules, Bohr calculated the very wavelengths of that light. The match was perfect. For the first time in history, a human being had deduced a fundamental law of nature from pure theory and seen it reflected perfectly in the light of the cosmos. The physics community was split. Older guards like Lord Rayleigh were baffled, but the young revolutionaries, Einstein, Fermi, Born, saw it for what it was: a breathtaking leap into the unknown. Bohr had drawn the first true map of the atom, and for this he received the 1922 Nobel Prize in Physics. Yet, even at his moment of triumph, Bohr knew his model was a bridge, not a destination. It was a hybrid, stitching quantum ideas onto a classical picture of orbits. A deeper, stranger truth was waiting, and to find it, Bohr would need to build not just a theory, but a sanctuary for thought itself, an institute where the next generation could confront the gathering quantum storm. He had solved one paradox to unveil an even greater one. Light could be a wave and a particle. Matter seemed solid, yet electrons jumped like ghosts. The foundation of reality was cracking, and at his new institute in Copenhagen, Bohr would gather the world's brightest minds to navigate the rubble, leading to a philosophical principle so shocking it would pit him in an epic, decades-long duel with his friend, Albert Einstein. Act 3. Copenhagen, the Mind Forge, and the Clash of Titans. In 1921, the University of Copenhagen inaugurated the Institute for Theoretical Physics, built specifically for Bohr. His vision was unique. This wouldn't be an ivory tower for solitary genius, but a collaborative workshop, a mind forge, where theorists and experimenters worked by side to test ideas against reality. It was a roaring success. Young physicists like Werner Heisenberg, Wolfgang Pauli, and Paul Dirac flocked to Copenhagen, drawn by Bohr's unique blend of deep insight and relentless, probing conversation. A walk with Bohr could be an exhausting, exhilarating intellectual marathon, stretching long into the night as he worked through problems by talking them out, famously mumbling and searching for the precise words. From this crucible emerged the next revolution: quantum mechanics. The mid-1920s saw a flood of brilliant competing formalisms. Heisenberg gave us matrix mechanics with its unsettling uncertainty principle. Erwin Schrödinger offered wave mechanics with its comforting fluid equations. The mathematics worked, but what did it mean? The young physicists were lost in a philosophical fog. It was Bohr, the elder statesman, who stepped in to provide the interpretation. During a 1927 skiing holiday in Norway, he forged his master concept, the principle of complementarity. His insight was this: In the quantum realm, you cannot talk about what an electron is, only about what you do to it. Ask it a particle question, where is it, and you get a particle answer. Ask it a wave question, how does it interfere, and you get a wave answer. These two truths are mutually exclusive, yet both are necessary for a complete description. They are complementary. The act of measurement is not a passive reading of a pre-existing state. It is an active intervention that forces nature to choose one face to show. As Bohr put it, it is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. This profound, almost philosophical stance did not sit well with everyone. It sparked the most famous debate in the history of science. Albert Einstein, who believed in a deterministic, independent reality, despised the inherent randomness and observer dependence of Bohr's quantum world. God does not play dice with the universe, Einstein declared, to which Bohr famously retorted, Einstein, stop telling God what to do. Their battle raged for years at conferences, most famously through Einstein's clever thought experiments designed to trap quantum mechanics in a paradox. Each time, Bohr would stay up all night, filled with shivering dread, only to emerge at dawn having found a subtle flaw in Einstein's reasoning, defending his complementarity view. Bohr won every round on points, but Einstein never conceded the match. This respectful, monumental clash was the engine that drove quantum theory to greater clarity. It was a testament to Bohr's role not just as a discoverer, but as the deep interpreter, the philosopher king of the quantum realm. Yet, while these titans debated the nature of reality, a dark and tangible reality was descending upon Europe. The cozy international world of science was about to be shattered by war, and Bohr, a half-Jewish Dane living in an occupied nation, would find his philosophy of openness tested in the most brutal way imaginable, forcing him to make a midnight escape with Nazi agents on his heels. Act 4. War, Exile, and the Terrible Fire. The 1930s saw Bohr's Institute become a haven for physicists fleeing fascism. He used his influence and funds to help Jewish scientists escape. But in April 1940, the Nazis occupied Denmark. For 3 years, Bohr remained in Copenhagen, a symbol of Danish intellectual resistance, secretly helping the escape networks while the world assumed he was safe. But in September 1943, the Nazis decided to deport Danish Jews. Bohr, whose mother was Jewish, was now a target. He was tipped off just hours before the Gestapo raid. In a dramatic flight, he and his wife Margrethe were smuggled by the Danish resistance across the Øresund Strait to neutral Sweden in a small fishing boat. The story goes that in his haste, Bohr brought 2 crucial items: a bottle of heavy water, vital for nuclear research, and the Nobel Prize gold medals of 2 German physicists, Max von Ley and James Franck, that had been entrusted to him to hide from the Nazis. To avoid the medals being discovered, his friend and fellow scientist George de Hevesy dissolved them in aqua regia, where they sat innocently on a laboratory shelf throughout the war, later to be recovered and recast. From Sweden, Bohr was whisked to Britain and then to America, where he was given the pseudonym Nicholas Baker and brought into the heart of the Manhattan Project. His role was that of a father figure and sage consultant. He didn't lead the engineering, but he provided critical insights, most notably clarifying the design of the modulated neutron initiator, the crucial component that started the nuclear chain reaction at the precise moment. Yet, Bohr was haunted. He saw the bomb not just as a weapon to end a war, but as a revolution in human affairs that made future wars potentially unsurvivable. He embarked on a lonely, urgent political campaign. He met with Churchill and Roosevelt, arguing passionately that to avoid a post-war nuclear arms race, the Allies must share the basic science of the atomic bomb with their Soviet allies before it was used to build a foundation of trust and international control. He envisioned an open world where science transcended nationalism. The statesman thought him naive. Churchill, in particular, viewed his ideas with deep suspicion, even suggesting Bohr might be a security risk. Bohr was devastated when his warnings were ignored. The bombs fell on Hiroshima and Nagasaki, and the world entered the age of mutually assured destruction, just as he had feared. The man who had spent his life illuminating the invisible structure of matter now saw his knowledge ignite a sun on Earth. From the ashes of war, a weary but unbowed Bohr would return to Copenhagen, shifting his mission from unlocking atomic energy to ensuring it would never again be used to destroy, becoming the wise elder statesman for a terrified world. Act 5. The Elder Statesman, Advocate for an Open World. After the war, Bohr returned to his beloved institute in Copenhagen, which had survived the occupation. But he was a changed man. The theoretical physicist had become a global humanitarian. He devoted his immense moral authority to a crusade for peaceful international cooperation in science. He wrote public letters, gave speeches, and tirelessly advocated for what he called an open world, where nations would share scientific knowledge transparently to prevent secret, paranoid arms buildups. He didn't just talk, he built. Bohr was instrumental in founding major European scientific collaborations designed to transcend national borders. He played a key role in the establishment of CERN, the European Particle Physics Laboratory, and the Nordic Institute for Theoretical Physics. His dream was to turn the destructive potential of the nucleus into a force for good, clean atomic energy, advanced medicine, and deeper understanding. For his efforts, he received the first ever Atoms for Peace Award in 1957. At home in Denmark, he was a national treasure. He was awarded the Order of the Elephant, the country's highest honor, and his portrait graced the national currency. To the public, he was the gentle, wise professor with a pipe, a kind smile, and a famously impenetrable mumble. To scientists, he remained the oracle of Copenhagen, whose approval they sought and whose philosophical depth continued to inspire new generations. Niels Bohr died of heart failure in Copenhagen on November 18, 1962, at the age of 77. On the day of his death, physicists attending a conference in his honor stood in a moment of silence. One of them remarked that it was fitting. The conference had been discussing a newly discovered celestial object that emitted radiation in discrete, quantized bursts. They called it a pulsar. Even in the distant cosmos, the quantum rules Bohr helped unveil or making themselves known. Epilogue: The Enduring Echo. So what is the legacy of Niels Bohr? It is monumental and multifaceted. Scientifically, his Bohr model, though superseded, was the essential first step into the quantum world. His Institute for Theoretical Physics was the incubator for modern physics. His principle of complementarity remains a cornerstone of how we interpret quantum mechanics, a fundamental lesson in the limits of classical language and the contextual nature of reality. Philosophically, he taught us that profound knowledge often comes not from choosing between contradictory truths, but from holding them both. He showed that in science, clarity and truth, Klarheit und Wahrheit, must constantly be balanced. Humanistically, his life is a powerful narrative of moral courage, from saving colleagues from the Nazis, to his desperate flight from occupation, to his principled, if unsuccessful, campaign for nuclear transparency. He grappled with the ethical weight of discovery more deeply than perhaps any scientist before him. In the end, Niels Bohr was more than a physicist. He was a navigator of the unseen, a cartographer of the impossibly small, and a visionary who understood that the lessons of the quantum world, interconnection, complementarity, the role of the observer, might just hold wisdom for how we build our human world. He looked into the heart of the atom and saw not just a nucleus, but a reflection of our own complex, contradictory, and wondrous existence. His story ends as it began, in Copenhagen, but the conversation he started, about the quantum, about responsibility, about reality itself, echoes on, as vital and unsettled as ever.